really excited to be here today. Thank you for having me. And I hear you've had an amazing day of water design, understanding the treatment process, understanding the engineering design principles. And I'm really excited to be able to talk to you about my experiences with water today and relate them back to some of the things that you will have learned throughout the day. My name is Sanjay, and I am a water engineer. And I will cover what some of the different disciplines in water engineering part of the way through. But essentially, the underlying physics, mathematics is all the foundation to an engineering principles. And it's the decision making that goes on top of that that turns the underlying formulas and the foundation into engineering design principles. So it always requires a human to be able to make these decisions. And as you will have found from doing the design lab, that there are so many different ways that a treatment process or this design could play out. But it all comes down to thinking about the underlying business goal and how that relates to the outcome. So one thing with water, and this is what got me really interested when I first fell into the role, and I'll explain how I got there as well. But when you turned on the tap this morning, water came out. When you flush the toilet, when you have a shower, the water just gets taken away. And it's really easy to take for granted how that water gets there or how that water gets taken away. You imagine waking up in the morning, turning on the tap, and no water coming out. It changes the whole way that you think about that engineering principles that go to get that water to your system. So I had the experience when I was growing up when my origins are from India, and my parents took me back but I was born in New Zealand. My parents took me to India and back to the village where my grandparents grew up. They migrated to New Zealand in about the 1920s. And this was in about 2000, they took me there. And I was very unaware of how people are still living these days around the world. And this village that they took me back to, which is where my grandparents grew up, still didn't have a constant supply of water. They had one tap that fed the entire village, and water would only come out of that tap between the hours of 6 a.m. and 8 a.m. each day. So each morning, we had some helpers that were there that were making sure that we would survive in the village. But this was in the year 2000, so not that long ago. It might have been a while ago for some of you kids. You may not have been born. But when I was there, it was very eye-opening. And you turn up, wake up in the morning, some helpers go and get the water. They fill up buckets from 6 a.m. to 8 a.m., store those for the rest of the day, and then have to apportion that water accordingly based on the day's usage. They have to make sure there's enough for the dinner preparation. They have to make sure there's enough to clean your hands, to have a shower, to drink and rehydrate. And you had to be very, very careful about its usage, spilling it. There was no other way to get water back into the city unless you collected it and saved it up for the day. So you think about that in your daily life. What if you had to get up in the morning and collect the water for the day, store it, and then use it from barrels or buckets? We have the luxury of turning taps on and having that water getting taken away all through the underlying infrastructure. So that's one part of the water engineering principle, getting water to a city. But there are so many other aspects. And you think about that as you're designing things as well. Everything that comes through the engineering design principle is making life easier for today. And it's very easy to sort of forget about these underlying pipes that are unseen underground that are supplying the world's most precious resource. The other thing that I want to get across is that every city in the world that gets inhabited, the very, very first thing that has to be made sure is you have to have a decent water supply. It is the primary reason why places in the world get inhabited. if you don't have that primary water supply, you can't live there because you just don't have the basic necessity to live, more so than electricity, more so than fire. So being able to hydrate, and that's what really gets me interested with water, that it's the basic necessity. Okay, so these are the things I'm going to cover today. And hopefully I got passed through some of the questions that were provided up front. And I was very impressed, by the way, to have, I wish I had had that understanding and experience when I was at high school. But to have those questions come through from high school students, I was, very impressed. So I'll try and cover those as part of some of the slides that I'll be covering today, but happy to answer more of them later on. And I'm sure Betsy would have answered some of them earlier in the day as well. So I fell into water. And what that means is that it wasn't my core passion, but I really enjoyed and followed my passion with the subjects that I was doing at high school. Maths, physics, chemistry, sciences. And that's what got me into the engineering discipline. And I studied at the University of Auckland. So what I want to get across here is that if you're following your passion, you don't necessarily have to know exactly what you want to do when you leave school. But keeping in mind that whatever you're doing, you need to enjoy it. And so I went into the engineering discipline, still not really knowing what an engineer was. And this is what got me really involved with Engineering Tomorrow, that I wish I'd had people talking to me about what engineering was, what engineers did, prior to me even joining the engineering discipline. But I went through the engineering program and did a discipline called engineering science. And that was really computer programming, optimization, looking at networks and flow of water or electricity or anything oil, anything that has sort of hydraulics or networks associated with it. The engineering discipline is very versatile. It's taken me around the world. Like I mentioned, I grew up in New Zealand. I lived in Belgium for a few years and was able to carry on my engineering discipline there. And also was living in the US for about 8 years. I only moved back to New Zealand last year. But when I was living in the US, I was in Philadelphia and in DC. But all to say that the skills that you learn can be globally applied. While there are some nuances and intricacies in different regions of the world, different standards, different practices, the underlying principles are the same. And it's the using the foundational skills, so the maths and the physics, to understand trade-offs and the business goal that come into play with every sort of decision. And when you're designing these, the treatment processes or the actual design for what you've done earlier today, it's understanding there are certain regions of the world that have lower access to money or don't have the same sort of income as different parts of the world. So you have to design these in a way that is affordable to the people who are using it. You can go all out and put all of the material that you have into a filter, and it may clean the water even more so than the design that you came up with, but it comes at a bigger cost. So those trade-offs are more important, and understanding the impacts to the people who are using it than the actual design itself. And that's where that the engineering concepts come in. Okay, so I'm just going to cover a few things about water and then get into a few of the projects that I've been working on. But you've probably seen this a version of this slide before, but water, the amount of water in the world at the moment is finite. It's not going to go away. It's not going to get lost, but it takes different forms. And it's how it gets around the system that water engineers are really responsible for. The cost of getting it from a source to treatment to a consumer when you turn on the tap plays a big role. Even though it's going to keep going around the system, people are going to use it. It's going to go to a collection system. It's going to fall down in rain, go down stormwaters, get back into the original forms. It still goes around the cycles, and making sure that it's in the right regions at the right times is really critical as well. For example, you could draw it from an underground storage location, have it used, have that collection water pumped to a different part of the city, dumped back into a lake in a different area, and then slowly you're going to deplete the groundwater storage that you pulled it out from. Unless there's more rainfall that happens there, unless you start taking care of the resources that you pull it from, that's when you start to get into a bit of trouble. And one of the stories that I'm going to tell a little later is to do with the South Africa Cape Town situation, where they actually ran out of water and they were very, very close to this entire city not having any supply because of their overusage. But keep this in mind that it's finite, it moves around. We don't want to be moving it to places where it doesn't naturally come from, because that changes the whole dynamics of the earth. At the same time, taking into account cost, obviously. So a water engineer is responsible for all of those processes. You get the water, where the water originally comes from, the supply, goes to a treatment process. So you still have to have infrastructure that gets it from its original supply to the treatment process. The treatment process, which is what you were helping to design today and come up with new ways of trying to clean that water. Once it gets treated, it gets then put into pipes, reservoirs around the city, and when you turn on your taps, it comes out. So it's that whole collection network. And this little diagram on the right here is actually an entire city's underground network. It's the main pipes, not necessarily all the individual ones that go to households, but it follows the streets, and you have simulation models of these. And that is what my primary focus is in my current role at the moment, which I'll get into. Collection. So once you use that water, it starts going down the drains. Flush the toilet, it goes down. You have a shower, it goes down. You turn on the tap, it goes down the sink, and that gets taken away. You also have rainwater that falls on the streets, and that also gets taken away. So you have two concepts: the collection, where you have wastewater, which is water that you use, and there's stormwater that comes in from the ground, and that all gets taken away, sometimes in separate systems, sometimes in combined systems, and then treated again, and then put back into the environment. So that's another part of it, collection. Then you've got the flooding and the recycling. So understanding the flooding, that there are certain storms that come through, and we've just had a huge one here in Auckland the last few days, that we had 75% of the month's rainfall occur in 1 hour, and we've had houses that living areas go 1 foot, 2 foot underground. Some houses have been chest height in terms of the amount of water that have been in there, so huge amounts of damage. So you've got flooding that occurs there, and events like that are hard to design for because the city just doesn't have enough money to build the infrastructure to cater for these 100-year, 500-year storms. But it's all part of the engineering design. And then you've got the recycling, that water can go back through the treatment plant and get treated, but you also have local recycling. That water that you have that goes down the shower is considered grey water, for example, as opposed to wastewater. And that could be potentially used for flushing the toilet again. So there are all these little concepts that you can build around the system that take the pressure off the underlying infrastructure. And again, all part of the engineering design principles. Within each of these principles, you then get some very detailed understanding And one of the questions that came through that I was intrigued with was how much time do you spend in front of a computer versus how much hands-on? And my role predominantly is in front of a computer, but that's because I'm involved with the design process and the planning process before it gets to the actual physical construction of things. But there's a whole concept before that goes into research and development that is very hands-on. There's a whole concept even after that that's very hands-on, where you've got to be on site doing the construction. You've got to be touching the valves, the pipes, to make sure that the way that you've designed things or the way that you've chosen to piece things together is actually constructed correctly. And then obviously at the very end, once it's all built, you've got the operations and maintenance. And there's engineers associated with all of those parts along the system. So whether you choose to get into different water engineering roles here, you can then choose in amongst those. And however comfortable you are with hands-on, if you want to be more hands-on, if you want to be out in the field, there are all these roles that cater for those different preferences. So we've talked about cost a little bit here, and that certain parts of the world have more money than others. Certain cities in different countries have more money than others. That you always need to be designing the water parts of the city based on the amount of money that the residents in that city have. You have more affluent areas of the world, like Dubai, the Middle East, that don't necessarily have natural supplies of clean water. They don't have that many lakes. They don't have many rivers running through. But so they have to predominantly get most of their water through desalination. And so desalination is where you convert this seawater or salt water, a very intensive process to remove that salt from it to turn it into fresh water. The cost of desalination has come down. It used to be about 4 or 5 times the price of conventional gravity-fed treatment, but now it's down to about 2. So it's still more expensive, but you think about and I'm not too sure if many of you have the concept of understanding what the water bill comes to in your household. But if you were to double that, it has a big impact on everyone. Everyone uses water. Everyone has a water bill, and you double that, and the household costs jump significantly, and it's an ongoing cost. So the cost of desalination plays a part as to whether it's feasible to actually build in that city or not. Whether the technology is there, it's the decision of whether the residents in the city can actually afford it. Certain parts of the world have backup desalination plants, so they use conventional when necessary. And what you were building is more of a conventional treatment process. But in places where they have droughts every 5 to 10 years, they might have a desalination plant that turns on at times when they need it. So it lowers the cost. And those are all things that are thought out in advance in the designing. And then I also wanted to touch on aquifers. So in the first diagram, when it showed the water that goes around the system, you have these underground storage locations, and these are aquifers, and they're not seen. You think about different parts of the world that are really appealing to live, and beach houses, for example, lake houses, areas on the beach, high-rise buildings that overlook the water. The reason why these are really highly sought after is because water is aesthetically pleasing. So many things go, it's a nice lifestyle, boating, for example, swimming in the beach, but also just looking at it. You have water fountains around the city that usually serve not much more of a purpose than just they're nice to look at. Aquifers, on the other hand, are underground, they're not seen. And so there was a time when people were drawing from aquifers. It's pure water, and having them using that as the water for the source of the city. But it comes at a cost as well. One, it's not seen, so it's very easy to draw upon and not have residents of the city be aware of it. But If you draw too much, it actually has an impact on the geological lay of the land and causes some really big issues when that starts to get depleted and it's not being returned in the same way. So there are lots of places around the world that are now running into this issue, and a little too late. It's all come a little too late that they've started to observe those issues. But now it's becoming much more, there's a bigger awareness for it. I wanted to also touch upon some of the projects that I've been involved with. And so my role, I worked as for a software company when I was in New Zealand. When I moved to the US, I worked for CH2M or Jacobs Engineering, which is an engineering consultancy. And now over the last few years, I started a company with a co-founder in Chicago, and we are involved with using simulation models, using the underlying pipe networks and models of the system to better operate and plan for capital improvements, all using the power of simulation, machine learning, optimization, and the compute power that's now available. So a little bit of programming usually comes down to the planning and the engineering design principles. No matter how much compute power you throw at something, it's all to bring to the surface information that would help an engineer that's having to make decisions come to those right decisions and justify those decisions. What is it? What is the lowest cost? What are the impacts of the lowest cost solution? Does it actually treat the flooding, or does it actually supply the water to the system at the right times at that cost? Is there a lower cost way of doing that? Can we afford a little bit more? Can we actually build the capacity a little higher and cater for these 100-year storms or 500-year storms? Usually the answer is no, but you need to make sure you're making these decisions with the most informed information. And having models of the system, using machine learning, using the physics-based models of the system helps to address that. And that's what I'm doing at the moment. But one of the projects that we formed was looking at a wastewater treatment plant. And this example here shows the Blue Plains facility in DC, which is one of the biggest in the world. Knowing when you've got a treatment plant this size, there had to be a decision made by the people who were building it, companies that were building it, as to how big to make it. What are the trade-offs? One, you're taking up a lot of land. You're taking up a lot of land on the edge of a river. You are taking up land that could be used for residential purposes, could be used for sports stadiums, could be used for everything else. So the bigger you make it, the more capacity it can take. So the more it can treat that water, but it comes at a cost. And there's obviously the cost to build it, let alone those trade-offs. The amount of water that comes into this treatment plant comes from wastewater and from stormwater. The number of residents in the city is usually known and can be planned for in advance. And so all of that water comes to this facility. You have storms that occur, and all of that rainwater that falls onto the roads, falls into your gardens, goes down drains, and also comes to this facility. That the water that comes to this facility is treated, cleaned, not to the standard for drinking, but cleaned enough to put back into the environment, and then discharged back into the river. Okay, so that's the process of how it goes through. You then now need to design this water treatment plant to cater for that water that's coming in. Again, the residents are known, so you've got the right amount of wastewater, but the storms that come through the DC area and any part of the country for that instance are variable. And when you've got really big storms, you've got an overflow, and the amount of water that's coming to this water treatment plant is more than the capacity. So what happens? You don't have the capacity to treat it, so you have to discharge it into the environment untreated, uncleaned. And that is one of the things that the US is really hammering down on now, that most utilities that treat wastewater now have to abide really stringent measures to make sure that they're not discharging polluted water into these natural environments more than X times per year. So, for example, 1 or 2 times per year, you're allowed to do it. But if you have more than that, you're going to be paying fines and penalties. So you have to make sure you design this system or design this treatment plant to cater for those regulations that are put in place globally. One of the things we looked at here was, what are the alternative measures of building this treatment plant? If you didn't have the capacity to expand further, what other measures could you take? And then you start thinking about, okay, for individual houses, water falls onto the roof, goes down the drains, and then makes it into the stormwater and makes its way to this wastewater treatment plant. If you had green infrastructure, so green infrastructure is where it collects rainwater or stormwater and actually uses it for gardens, or is absorbed into the soil a little bit more rather than just running off onto concrete. But it's got a lot of aesthetically pleasing purposes, as well as the benefit of taking pressure off the water that comes to this wastewater treatment plant. Different parts of the cities have different underground networks that collect that water and bring it to this wastewater treatment plant. So the study that we did was to work out which parts of the city are most beneficial for the amount of rain that they get and reducing the amount of water that comes to the wastewater treatment plant, which means that you can downsize the wastewater treatment plant or at least not expand it. But it also means that you've got less water coming through and less chance of polluting the environment, because all of that water sort of stays closer to the houses, is used for growing gardens and actually growing flowers, vegetables, the trees. So there's double benefits associated with that. And because of that underground network that collects all that water and brings it to this wastewater treatment plant, there's variability in the size of those around the city. There's variability in the amount of rainfall that different parts of the city get. There are going to be parts of the city that are going to be better to incentivize than others to build green infrastructure or put green roofs on their houses or put something in their backyard that actually helps collect the water and reuse it. So if the utility is then funding some of these projects, they can then direct that funding towards these houses that are going to have the most benefit. So it's a really, to me, it's a really interesting problem. It takes into account hydraulics. It takes into account the cost of residents. It takes into account the incentives of the utilities that are having to make these decisions. It brings together all the mathematics and foundational physics with the pipe networks that go underground, simulation models, optimization, bring machine learning into that. It's a lot more complex than it sounds, but it helps to really understand what's going on in the actual city itself. One of my biggest passions, and this is where I've spent most of my engineering career, is in energy costs. The amount of water that you would use in a day is around about 100 gallons. One big barrel of oil, so the standard barrels that you see wine come in, that oils come in when someone talks about a barrel, that's about 42 gallons of water. 2 of those is the amount of water that you individually would use on average per day. You think about carrying that water from the source. Let's say you've got a lake that's, like 5 miles away is probably pretty close. But if you were to have to carry or roll that 2 barrels of that water from a lake that might have been 5 miles away, roll that or carry that back to your house and then use it, the amount of energy to get those barrels to your house is exactly what has to happen in an underground network. You've got pipes that do it, which make it a lot easier, but that's essentially what happens. Someone is pumping water, or the utility is pumping water from its original source to get to your tap. And that requires the energy. You have some parts of the world where it's a lot easier to get to because that lake might be up on a hill. And then you can just let it roll down. You can let the barrels roll down the hill to your house. Similarly, you can let the pipe will bring water down to that house just through gravity. But most of the time, it has to be pumped across the city to get to those individual households. So the amount of energy that's actually used in the US to transport or just collect water is around 3% of the entire nation's energy usage. That's, you think about that, and 3% may not sound like much, but just for transporting water around the system, it's in the trillions of dollars. The hydraulics associated with that is what I've mostly been focusing on. When to turn those pumps on to actually distribute that water at times when it's lowest cost. Can you fill reservoirs that are up on a high hill at lower cost times of the day? So at night, for example, when the electricity cost might be cheaper, let that drain throughout the day. So that's from an operational perspective. How do you operate those pumps at lowest cost? And then you've got the amount of pressure in the pipes. If you're pumping a huge amount of water, the pressure in the pipes increases, which means you're pumping up against a lot more head, which means it costs. There's more energy required to push it along that pipe when there's lots of water running through it than when there's not. So that's just the basic understanding of the energy costs. But you think about that in real time, these water utilities are having to distribute this water and maintain these costs. There are operators who sit in the control room who are turning on these pumps, opening up valves to make sure that water gets around the system. And they're just making sure the water gets there, making sure that the water is there when you turn on the tap. But there's energy costs associated with that as well. This also comes into play when you're designing the system from scratch. What sort of pumps should you use? Should I be designing reservoirs in areas where there are hills that I can make use of gravity, for example? So energy costs is one of my passions, and that's what really gets me excited. It's a tricky problem. There's lots of dynamics that go into it. And then just want to touch on, I wasn't in Cape Town at the time, but I did meet a colleague while I was in the US who was from Cape Town. But what happened back in 2018 is Cape Town they pretty much ran out of water. It's the first time in quite a while that a city has actually run out of water, especially a developed city like Cape Town. But they were 6 days away from the entire city not having any water to drink. And the picture above here is of people lining up in the days beforehand to give their allocation of water. It goes back to what was happening in the village that I visited when I was in India, that I was originally from. You had people lining up for their water supply for the day. The issue here was that in Cape Town, if rain hadn't come in 6 days, they wouldn't have even had water available at times of the day to be able to collect this water. It would have been completely devastating. All the residents of the city, like, what can you do without water? You need it for drinking, you need it for living. Luckily, rain came through Cape Town and filled up their reservoirs, and now they're in a better state. But it got the entire world thinking about how to better manage this resource, how to make sure situations like this don't happen again, how to build in redundancy to make sure that you can get water supply from a different region into the area should something like that happen. Maybe a desalination plant, only in the case of situations like this. People would be willing to pay triple the price for water just to make sure they had it. So it's a big trade-off. The guy that I met who came from Cape Town back in 2018 had mentioned that their whole way of living had changed. They were taking showers and collecting that water in a little tarpaulin in the shower. Once they had finished the shower, they'd collect that water and put it into a storage container, use that for flushing the toilet. So their whole water usage appreciation was brought to the surface. And now he said they'll probably be implementing that for a while. One, because it's better for the environment, but two, they don't want this situation to happen again. So it's not until you experience or have to go through something like flooding, for example, that happened here, or Cape Town, where they ran out of water, that you start to appreciate all that underground network and the supply and the engineering design principles that go into making a city work.